Welcome to Programming Languages for Civil Engineering students. In this video, I will explain very simple design of the footing, the isolated footing. Okay, and I will briefly explain what is the procedure. Perhaps everybody knows. You can refer to any standard, any RCC books for deeper knowledge. Okay, at present I will explain a brief. Then I already implemented the design of isolated footing in Fortran programming language. Okay, first let me explain briefly. The question is, you can see here, the reinforced concrete column of size 300 mm by 300 mm carries a load of 750 kilonewton. The safe bearing capacity of the soil is 200 kilonewton per meter square. Design an isolated column footing with a uniform thickness. Okay, use M20 grade and grade of steel is 415, Fe 415 steel. Okay, these are the data. In question, the axial service load had given, the size of the column had given, and SBC, that is soil bearing capacity of the soil, is given, and FCK, grade of concrete, is given, and grade of steel is given. Okay, everything is provided here. Okay, then then problem starts from here. You can see here, the problem starts from here. The size of the footing load from the column already given, P is equal to capital P 750 kilonewton. Then self weight of the footing, that is 10% of column load, that is 75 kilonewton. The total load on the column, that is 825, that is 750 plus 75 is equal to 825. Then area of the footing, if you want to find the area of the footing, then we have to divide total load by SBC of soil, that is soil bearing capacity of the soil. The total load is 825 kilonewton by SBC of the soil, that is soil bearing capacity of the soil, that is 200 kilonewton per meter square. Then kilonewton cancel, and by square, that is it will comes to 4.125 meter. Then we have already obtained, this is the area of the footing. If we want, let us say I am taking square feeting, so you have to square root. You can see here B is equal to root of 4.125, that is 2.03. Let us say adapt to 2.1 cross, that is 2.1 by 2.1 square footing, meter square footing. Then upward soil pressure, we want to find the upward soil pressure. The factor load, we have to give factor load because we are using limit state method. So PU is equal to 1.5 into 750, that is 1125 kilonewton. And soil pressure at ultimate load. Okay, generally we know the ultimate load, PU ultimate, that is PU by area of the footing. Then you will get soil pressure which is acting upward towards the footing. Then that is 0.255 Newton per mm square. You can see here. Then after the depth of footing from bend, we have to calculate the depth of footing from bending moment consideration. You can see here, this is our square footing. Okay, this is the column, and this is the critical section. The critical section is, you can see here, the critical section for bending moment, just like the cantilever slab, it will act like a cantilever slab. Then we already know the width, the width of the footing, or dimensions of the footing is 2.1 cross 2.1 meter. Okay, then 2100, we want only this area, only this hatched area. So what we have to do means, we have to divide, we have to subtract this column width by 2, then we will get 900 mm. This is the critical section. We already know mu is equal to Q b of b minus b square, small b square by 8. And after calculating, then we will get this 216.88 into 10 power 6. Then we have to calculate our mu. From here we can calculate what is our mu. Then we already know mu is equal to 0.138 fck bit square for 415 grade of concrete. For different grade of concrete, there are different value. This 0.138. This is the function of this constant is the function of grade of steel. Okay, then after substituting all this, we will get the depth of the footing, that is depth 193.4 mm. The depth required to resist shear footing, shear in footings is much higher than the required for bending. So we let us assume the effective depth is twice as the depth required. This is the effective depth. Then we have to effective depth is equal to 2 into 193.4. We will get 386 mm. Let us adapt 400 mm the effective depth. Let us say the clear cover of the footing is 50, that is totally 450 mm overall depth to take care of shear. The reinforcement, we already know this is the formula, and by solving the quadratic equation, then you will get two values. One is higher and minimum. We can take minimum value, okay, using 12 mm. Let us say 12 mm by diameter. Then spacing of the bars is 150. Let us adapt 150 mm. Okay, use 12 mm main bars at the 150 mm. But check for one way shear. This is the formula. Check for one way shear. Okay, check for two way shear. Okay, then check for development. Everything is as usual. We know. Please refer to any of the standard textbooks. Okay. Then coming to the original thing, let us once. I already developed a code. This is the code I developed. A program that is isolated footing design, IS 456-2000 limit state method. Okay. By using this code, I have developed a code. This is a generalized code. Okay, you can use for any number of any grade of concrete or any type of grade of steel. Okay, you can see here. This is the code. And let us say once what is our input. Our input is axial load. We have discussed some axial load. Then SBC, that is 200 mm square, 200 kilonewton per meter square. Then breadth of the square column, that is square column, generally 300 mm. Then FCK and F5, then diameter of the mere bar. Okay, these are the input. We have to give the input. This is the input file. Then after that, we have to run the program. Just you can save and just you run the program. Then we got the program has performed the task. Then the output is shown in this. You can see here. This is the output. You can see here. This is the. I will explain. You can see here. You can see here, this is the upward soil pressure, all these calculations. Okay, you can see these are the calculations, the depth of the footing and bending moment consideration, all this design. Okay, all these are things. Provide the effective depth of footing is in mm, that is 384. Let us say that 400, and provide the overall depth of the footing, that is 434.76 mm. Okay, then reinforcement details. Provide the diameter of the main bar is 12, and spacing of the bars in mm, that is 147.36. Then let us say we can assume for 150, you can select. And spacing, the spacing of the bars is 147.369. Let us say we can take for 150. So check for one ways here. This is the critical section, already we discussed. If you have any doubts, please refer to any standard design textbooks. Okay, then hence it is in a hence it is safe with respect to the respect to two ways here. Then check for development. The development length is 54 and development is sufficient, hence it is okay. Okay, development is also sufficient. Check for bearing pressure, hence it is safe with respect to bearing. We have already checked with bearings bearing pressure also. Final results of isolated building. You can see depth of the footing 434, total depth of the footing. Let us we assume some 450. The spacing of the parts 147. Let us assume 150 center to center. The diameter of the main parts is 12 mm. Hence it is safe with respect to one ways here and all two ways here, and also bearing checking for bearing. Hence it is safe with respect to bearing also. Okay, this is the way. You can see here, this is critical section, this is diagram, and you can see here this is the critical section. All this we can use we can generate this kind of things by using this Fortran programming language. This is only a simple thing, but if you are habituated, then you can do any number of things by using this Fortran programming language. Okay, this is the brief about design of isolated footing. Okay, anyway, thank you for watching this video. Thank you.